So, good evening. I will be closing this session, and so I decided to present to you some ideas with the lowest possible level of sophistication in mathematics. You already had a bunch of sophisticated expressions, so I will not tire you. I will keep things to the bare minimum, and I will discuss something about the notion of composite systems. This is an ongoing work with Alberto, Ibort, and Giuseppe Marmo, and it's so ongoing that the presentation I will give you is based on notes that we kept writing until 3 days ago. So it's a slight improvement with respect to the paper that you find in the proceedings. And the work is not done yet, so it's still going on. So any suggestion is, of course, welcome. So the talk is based in 3 parts. It's divided in 3 parts. A quick introduction, where I just recall how to deal with composite systems in the classical case, in the quantum case, and in the context of C-star algebras, with which you can obtain quantum and classical case in one shot. Then I will pass to a more general framework, which could be called convex framework, which is based on the idealization of an experiment as made up of a state preparation and some experiment, so registration of some experimental outcome. And it is in this framework that I will try to address the question of what is a composite system and essentially why we need the tensor product. So, first case, probability distribution. We have a sample space with this sigma algebra, we already know, and the states are just probability distributions. How do we manage composite systems? We take just the probability distributions on the product space endowed with the sigma algebra, which is the tensor product of the sigma algebras. And the simplest example is that of 2 simplexes that you build up together to obtain a 3 simplex. Okay. In the quantum case, we have a Hilbert space of states, which is the space of density operators on the Hilbert space of the system. So operators that are positive, self-adjoint, and with trace equal to 1. This set, just as this one, is convex, and this is important. And we handle composite system by taking the tensor product of the Hilbert space and then building the space of states, just as we did for the single particle case. In this case, there is no graphical representation because the simplest example lives in a 16-dimensional space, so it's quite hard to picture. And we can condense these 2 pictures together by using the formalism of C-star algebras, which was introduced very nicely by Jan 2 talks ago. So I will go fast on this. In this case, we handle composite system. Well, but this is kind of redundant now, because we already know that we can recover the classical case by taking the algebra to be commutative, like continuous function on a locally compact Hausdorff space, or as the algebra of bounded functions on a measure space. The quantum case, on the other hand, is recovered when the algebra is just the algebra of bounded operators on the Hilbert space. So in this case, we handle composite system by taking the tensor product of the algebras and then building the space of states. So the question is clear now, why the tensor product? In all these cases, to handle composite systems, we need the tensor product. So the question is, are there some physical assumptions behind the notion of tensor product that we are using? I will try to give a rough and partial answer to that based on the convex framework. As I told you, this is a very basic way of looking at systems. Just as we do in an experiment, we prepare the system and we register the outcome of some test. And I will base all the analysis on 2 assumptions. So the existence of independent states and independent experimental tests, and the assumption of the statistical independence of what? Of the independent tests performed on independent states. I will be clearer in a minute, I hope. So, first of all, what are states? in this very, very general framework, we can think of states as being related to preparation procedures. So we prepare our system. But it's not true that to each preparation procedure, we can associate one single state. There could be different preparation procedure that leads to the same state with respect to the outcome of measurement, so to the statistic of the experiment. So states are actually equivalence classes of preparation procedures. But it's true that preparation procedure may be mixed. So suppose you have two preparation procedures, and I flip a coin. If it's head, I use one. If it's tail, I use the other one. That's a mixing of preparation procedure, which is allowed. In this case, it was very trivial because it's half-half, but you can invent different ways of mixing preparation procedures. And we assume that this mixing operation is that of a convex set, which means a lot, but we will take this for granted. The point is that we know that states now are equivalence classes of preparation procedures, so we want this mixing operation, which is at the level of preparation procedures, to go down to the quotient and become a convex structure on the space of states. This is compatible with all the examples that we saw, so probability measures and quantum states in the standard framework and in the C-star algebraic one. For simplicity, I will take convex sets in a finite dimensional vector space, and I will assume the existence of a linear functional of this on this vector space, which is particular because it's constant on this convex set. So you can think of it as an analog of the identity function. So before entering introducing the notion of test, we need the notion of effect, which is just a mathematical one at this point, but it will be clearer later. So a test is just a linear functional on the vector space generated by the convex set of states, which takes values between 0 and 1. The fact that these values are here is related with the statistical interpretation of this framework. So any linear functional obeying this condition is called an effect. And the space of effects is denoted like this, and it's clearly a convex subset. And you can prove that the dual space, infinite dimension, of course, of the vector space generated by the set of states is just the vector space generated by the effects. So now, what is an experimental test? In layman terms, experimental tests are performed on states, on preparation procedures, to obtain a readable outcome. So we have to measure, and we have to test. Think of like yes/no questions, like my system has this property, yes or no. That's a very fair test, and this is enough. So I define a test as a collection of effects. So I take just discrete collections. For simplicity, I could also take actually collection of yes/no questions, so where the discrete number is just 2. Any value of j is just a way to label the outcome of your measurement process. And the compatibility condition is that they must sum up to give this particular linear functional, which is constant on the space of states. And the reason for that is given by this line, which could be thought of as an abstract version of Bond's rule in quantum mechanics. So we interpret what the number that we obtain by performing what the test E on the state rho as the probability. We consider the real number that we obtain by evaluating the effect E sub j on rho as the probability of obtaining the outcome j when we perform the test E on the state rho. So if you translate all this in the standard case of quantum mechanics, that's Bond's rule. If you translate it in the context of probability measures, that's the expectation value. So how can we build a composite system having these ingredients? So where are the physical assumptions that lead to tensor product in this context? So we start with two systems, S1 and S2. And we will work only with bipartite systems because the extension to the multipartite case is easy, straightforward, but it adds a lot of notational complications. So it was not suitable for this talk. But we must consider always indistinguishable parties. Of course, I was wrong here. We need to be able to discriminate between the two parties. So we are not considering fermions or bosons, because that would add an extra layer of complication. So we don't want to enter into this for the moment. So the first idea I told you is related about the existence of preparation procedures and tests that are somehow independent. So we want to formalize the idea that we have these two parties, and they are able, if they want, to prepare any states in their private space of states as they want. So we must introduce the existence of a map which takes the Cartesian product of the two space of states inside the space of states of the composite system that we would like to describe. And this map should be injective, otherwise it makes no sense. We have no possibility of building any kind of state freely in our private space. And similarly, we should be able to, the two parties should be able to perform any experimental test they want, as long as this test is allowed by their single party theory. So we must require the existence of an injective map now that goes from the Cartesian product of the space of effects into the space of effects of the full system. And we define a composite test just by considering the action, the test related by, obtained by considering the image of these two tests inside the space of effects of the composite system. So I think these are rather reasonable assumptions. You may, of course, not agree with that, because you may say, no, when you consider a composite system, the very fact of considering composite system does not allow to the free parties to prepare their states as they want. But yeah, that would be a nice way to follow. But I would not know how to address the problem in that case. And from the operational point of view, that's what happens. So people, for instance, in quantum optics, they are able to manipulate their systems independently. So this is a realized situation. Now we come to the crucial ingredient, the last crucial ingredient, which is just the statistical independence that we want when we perform what? When we perform a composite test, an independent composite test, on an independent composite state. So if the two parties want to perform each on their own this test on their freely prepared states, then the overall probability should be just the product of the two probabilities. So the two events should not influence each other. If you agree, for instance, if one of the two tests on the, let's say on the first party, is always 0 when you want to check the outcome J, then this probability must be 0, because when they perform the test together, one of them will never get the outcome K. So it's clear that the full system to obtain the probability of obtaining the outcome J and K should be 0. So this is consistent with this kind of picture. And this is essentially enough. So this is enough to do what? To witness the definition of separable states and entangled states, and to witness the appearance of the tensor product. And the first point may feel like cheating, but from a mathematical point of view, you are allowed to do that. So remember that we have this space. So this guy generates a vector space, and this other guy generates a vector space. And this set lies in a vector space. So what we can do is we can use the linear structure of the target space to define an action of now the whole vector space V1 star cross V2 star. So since we require this multiplicative behavior of the probabilities, we are able to extend the map from the product of the space of effects to the whole space of vector spaces generated by the effects. And we do it because of the multiplicative behavior of this object. We do it bilinearly. So it's the linearity on one part and the multiplicative side of this statistical independence assumption that lead to bilinearity here. And this bilinearity, as you might guess, is immediately going to tensor product I will show you how, and it will be really trivial. But before doing that, let's look at how can we define in this framework states that we might call separable or entangled. So first, we consider the elements which are in the image of this product space by means of this map. And we call these elements simple. So for instance, these are just couples. You can think of that as couples of vectors generated by effects. At this moment, they have no physical interpretation. They are just a mathematical consequence of our assumptions. And we call a state in the composite system to be finitely separable if it can be written in this way. So if I give you a simple element, and the action of this simple element, which is in the dual space of the vector space generated by states, on this state that we call finitely separable, can be written in this way, which means essentially that you would be able to write your state rho as lambda rho 1 tensor rho 2 plus 1 minus lambda, and I don't know how to do that fancy rho, so I will use sigma, like this. And this is the convex sum in the space of states of the composite system. This is essentially what you do in
It's twice the same. It's written there.
well, this is a fancy row, which I am realizing that the font and the color I choose are the wrongest ever. I never had such a bad quality of slides, but there is always a first time, so I'm sorry for you. But so this is a curly fancy row. So this would read, this is essentially how you would read it in quantum mechanics, if tensor product were already there. But in this case, it's not there, and you can do it nonetheless. Now, the separable states would be now in the closure of the set of finitely separable states. And here, you might say immediately, okay, in the closure with respect to which topology? You didn't speak of topology, you didn't give me some, and that's true. The act of defining separable states in this way is model dependent. So it depends on the actual model you are considering. If you are considering quantum mechanics, for instance, then you should take a topology which is related with weak star topology of a dual space. But you can do it just model dependent. And as this is model dependent, also the definition of entangled states, which are just the complement of separable states, will be model dependent. And in fact, if you want to model somehow classical probability, you should arrive at a point in which separable states fill the space of states of the composite system, and there is no room for entangled states. So these two steps, you may only take them once you have a model, an explicit model. So how do tensor product appear? Well, we want just to prove what? That the linear span of the image of this of the Cartesian product of these two vector spaces is isomorphic to the tensor product. And to do that, we will exploit just the universal property of the tensor product. So we have this product space, and we consider any other vector space X and a bilinear map from this space here. We will use the universal property of the tensor product by doing what? By constructing a linear map from this vector space W, which is just a linear span of simple elements, into the space X in such a way that this diagram commutes. If you are able to do that, then the universal property of the algebraic tensor product ensure that this guy is actually isomorphic to this tensor product. And this map here is essentially already here, because we have the little phi, which is a bilinear map from here to here. So what we can do, we can consider a simple element, which is in this part of the diagram, which is in one-to-one correspondence with an element in this part of the diagram. And we define the big phi on this F just as the composition of what? Of the little phi on this couple. And since the simple elements generate I'm already there. Generates the full linear space W, then this map may be extended in a unique way. Why? Because simple elements are a generating set for this vector space. And that's it. Since this map is there and it's unique, then we proved that what? We proved that for a composite system, obeying the assumptions that we saw, the dual space of the vector space generated by states must contain a copy of this tensor product. So just as it happened before, it's not the space of states that's related with the tensor product, but it's some auxiliary space or element that is related with tensor product. Now, in finite dimension, you can prove what? That this W, which is the tensor product of dual spaces, is just the dual space of the tensor product. This, in infinite dimension, is not always true and, of course, brings with it a lot of problems. And if we impose a minimality condition, so we ask that actually the dual space of our system is not bigger than the linear span of the simple elements, then we can conclude that the space of the vector space generated by the states of our system is precisely this tensor product. But even if you are here, you don't know who is S, so the actual space of states. And here again, you have to go model by model at this point. So you can either define S as the closed convex hull of the set of product state and then compute the space of Fx. Or you can do something different. You switch the perspective and you define the space of effect as the closed convex hull of the simple elements and compute then S, so the space of states, or you can do whatever it is in between. But if I was able to convey the message is that if you want to do something like that, then you still have to add some physical motivation behind your choice that explain why you are choosing between one of these alternatives. And with this, I finish and I thank you.
Yeah, we have time for some questions, please.
Okay, so I don't work in this area, but I just recall that reading some monographs on this convex
Operational
approach to quantum
yeah.
mechanics. So there are like standard textbooks, there are standard like reprints of older books and stuff. So I want to see what is your contribution.
This point here this axiom, the fact that you are imposing, because what they do in GPT is just, okay, I have the state of one system, the state of the other system, and the state of the product system will live in a tensor product space. And then that's it. And then everything follows. But in there, the assumption that the space of states of the composite system sits inside the tensor product of the vector spaces generated by the convex set of the subsystems is given. So it's like God-given. We want that. And what is the purpose of this contribution is to show that if you assume this statistical independence, which has a physical root, you cannot easily conclude that this is the case. You can have other situations that are not explored.
You assume statistical independence.
Yes.
But a lot of measurements are statistical not independent.
Yeah, in fact.
Yeah, so
But at least we agree that there are some that are independent, right? And that's enough to do everything else. So it somehow, at least in my head, clarifies the reason why you need this to obtain tensor product and shows that it's not the end of the story. So even if you rely on this, you cannot single out tensor product uniquely.
But the quantum system, the signature of that is not statistical independence. There's
Well, if you use product state and product measurements, then you have statistical independence. So you can always use a state like that. And you can always use an operator which is like that. And these two, and regarding to this couple, the statistic is just independent. It's when you consider an element which cannot be factorized like this that weird things happen. And that's precisely the feature of quantum mechanics. But also there are other systems
I'm
which...
not the expert on this stuff anyway. So.
Other questions?
Very nice presentation. Very nice, the way you put it together. Yeah, are your simple states what in the non-operational way would be the pure states?
No. There are pure states that are like this, of course, but purity requires a further step. So when I was here, I said, okay, let's just take a convex set in a vector space. If I give you a convex set, it's not said that there are pure states for it. So there exists convex set without pure states. Very simple example is just this kind of object. So it will be a simplex where I remove these 2 points. This is a convex set without pure states. So introducing pure states seems to be an additional requirement. For instance, if you require your convex set to be compact, then Klein-Millman theorem implies that there are convex pure states. But you have to add this assumption.
You can put logic in it.
Yeah, that would be very nice, and that's why the tests and the idea of this yes/no measurement, which is really old school.
What logic do you have in mind?
Well, Boolean logic.
Or quantum? No.
Or quantum. Yeah, so that's
Like Birkhoff or Neumann or
Okay.
Auto module.
Yeah, yeah.
So urgent questions anymore? Then I want to close the session. Thank you, speaker again.